Thank you for joining our July webinar. My name is Chen. Join me with Kevin, who is a senior founding engineer in Timeplus and focusing on Kubernetes infrastructure and also Timeplus web server and Timeplus web console.
Thanks, Ken.
Today we have quite a few things to go through with you. And first of all, Calvin will do the auto-scaling and Materialized View demo in Kubernetes. And I'll go through the long-awaited feature, schedule task. And lastly, I'll go through the new enhancement functions and also performance improvement in Timeplus Enterprise. In case you are new to Timeplus, Timeplus is a new unified real-time data processing pipeline which can do streaming transformation, streaming join, and streaming aggregation for different use cases like analytic, telemetry, and also AI. And our customers are usually using Timeplus as a front-end component to offload the real-time workload from your warehouses like ClickHouse and other data warehouses. Without further ado, I'll hand over to Kevin to demo the auto-scaling Materialized View in Kubernetes. Kevin, go for it.
Thank you, Ken. So this is Calvin. So today I'm going to demonstrate how we deploy Timeplus on Kubernetes and then how we scale it, how we auto scale it. And I will demo that mostly on our UI to basically show everyone some new exciting feature of our UI, how to use our UI to monitor the status of the Timeplus cluster. So before I jump into the demo, I'd like to describe the demo setup a little bit. So basically, this is the very typical pipeline use case. So first, we read the data from the data source, and then we have quite a few Materialized View to extract the common field. And then we write the structured data to a temporary stream so that other pipeline can consume in the future. And then we have a few filter Materialized View to filter out some of the data so that we can only write the most important data to the downstream. And the last, we have our downstream stream. As you can see, the first thing is this is on Kubernetes. So first, I will create a namespace, and then I will deploy Timeplus on that namespace. So we are using Helm to deploy here. It should be very straightforward, just a Helm install. And this is the values.yaml we use. I won't go through everything, but just highlight the key things we set up in our values.yaml. First is the resource we assign to our metadata node. And then the next is the compute node. So here I hard coded it to be 1, and then I will create some workload. And later on, I will enable the auto scaling. And you will see how we can easily auto scaling our compute node. So for now, it's commented out. And this is the resource we assign to the compute node. Okay, so I will start the deployment. So it's a very straightforward. It just run a Helm install. And okay, it's installed, and we will wait until the cluster is up and running. It's normally take a few minutes. So yeah, this is where the cluster is up and running, and we can check the cluster page. So this is the page we use to monitor the overall status of the Timeplus cluster. You can see a lot of metrics here, and you can see the node topology, the CPU, things like that. And as you can see on this screen, we have 1 compute node up and running, and we have 3 metadata nodes. Yeah, this is the setup, and those are the resources I created beforehand. So we have a source stream, which is the device matrix, and we have the structured data stream, and we have the final destination stream. And we can check the data lineage. So right now there are only 3 streams, and there's nothing connect between them. I will create the Materialized View to connect them later. And here I'm going to create the first filter Materialized View. I just create 1, and then I will create 1 extract Materialized View. And then you should be able to see everything is connected here. So yeah, I will just create 1 extract Materialized View. And then we can go back to our console, and you will see the CPU utilization start to increase. It was like 20 or something, and now it's increased to 74. So that means the Materialized View is processing the workload. And we can go to the data lineage to see the metrics here. And you can see there are metrics for each node. So that's how data flows inside our system. So the input rate is around 20 megabytes. And for the first screen, we extract some column. And that's why it writes fewer data to the next string. And after the filter, the throughput is even lower. That's because we filter out a lot of events. We only want to write the most critical events to the downstream. So this is a detailed view of the throughput of the destination stream. So right now it's around 300 kilobytes per second. So we will create more workload, and you can see this number increase in the later. Yeah, that's basically the first step. And the next, I will create more Materialized View. So that means we try to simulate more workload. And yeah, I create 2 filter MV, and I will create 6 extract Materialized View. So this is the extract Materialized View is the Materialized View that consume a lot of resource. Yeah, so again, it's yeah, let me create. Okay, and you will see the CPU utilization increase again. So it was like 60, and it will kind of hit the limit. So I only have 2 CPU aligned to compute node, and you can see this CPU utilization become 200 almost immediately. And at this moment, the system is throttled by the CPU, so that we hit the upper limit of what we can process. So right now the read throughput is around. If you look at the left side, the read throughput is around 70 per megabytes per second. And after the pipeline, you can see the final throughput to the destination is around 700 kilobytes. Again, that's because we filter a lot of data. So, and you can see the increase of the throughput here. It was 300, and now it's become like 600. So that's because we have more Materialized View to process the data. And it's not it's sorted by the CPU. So that's why we will enable the auto scaling, and you can see the increase. Here, yeah, it's very straightforward to enable the auto scaling. You just add this uncommented this section, the auto scaling section. Basically just enable it and set the minimal and the max replicas, and set the target CPU utilization. So this is the most important parameter you want to set here. So the target CPU utilization basically means how you want your system the CPU utilization of your system. So I set it to 70. That means I want my CPU utilization of my system to be as close to 70 as possible. And then Kubernetes, you will try to, it's pretty smart. You will try to adjust the number of replicas to make sure the CPU utilization stays as close to that number as possible. So then I will run the upgrade. This is basically a Helm upgrade. And then after the Helm upgrade, a new resource called HPA, which is a horizontal pod autoscaler. It will be created. And this HPA will kind of monitor the Kubernetes metrics, and then it will try to adjust the replicas. And here I didn't cut anything. You will see the another pod get up and running in just literally a few seconds. So let's wait for a few seconds. Okay. Yeah, now you can see one more pod is up and running. So the CPU utilization is increased to more than 100. And you can see the running MV. It basically we rebalance the MV. So right now, both pod 4 and port 5 has 4 running MV. So before the port 4 has 8 MVs. So that's our we kind of shift the workload from one node to another, and you can see the decrease of the CPU utilization here. So it's quite balanced here. And if we check the throughput of the overall system, and you will see the increase of the overall throughput. So the read side, it hits more than 100. It was something around I think 70 before. And if we check the throughput on the destination side, it also increase. So yeah, let's check. So it was like 600, and now it's something, it's 900. So that's basically demonstrate how fast we can leverage the Kubernetes to auto scale. Again, this is from the HPA perspective. So we scroll up a little bit. So you will see when we have only one replica, the average CPU is 99. It's way higher than target 70. So that's why it decided to create another replica for us. So that's why the replica increased from 1 to 2. And after we have 2 replicas, the average CPU utilization decreased a little bit. It becomes 70, which is very close to our target. So it will stay 2 for a while. And here I will drop all the MVs. And because after I drop all the MVs, there will be no workload. And you will see the decrease of the CPU utilization. And then the Kubernetes will, because the CPU utilization decrease, and the HPA, the Kubernetes horizontal pod autoscaler, it will basically terminate one of the pod. Because I obviously I don't need 2 pods up and running, right? So as you can see here, the pod is terminating, and the replica reduced from 2 to 1 again. Yeah, and on our UI, you can see node pod 5 is offline. So, and also on the diagram, you can see the node 5 is no longer here. Okay. Yeah, that's pretty much about my demo. Yeah, thanks everyone, and I will hand over back to Ken.
Yeah, so thank you, Kevin, for the cool demo. Timeplus auto-scaling Materialized View is very powerful and efficient to handle spiky workload, because you can auto-scale out and auto-scale in. And also Timeplus console is very handy as well to view and manage the data processing pipeline. So it is a go-to tool for our customers. So next, I do the demo for the scheduled task. So scheduled task is the demo scenario is just like I create a scheduled task. Scheduled task is just like a cron job, and which basically run some query, collect some data. It can periodically run some query, get some data, and also write the data to a target stream, Timeplus stream. And on the other hand, we can create a Timeplus alert. A Timeplus alert is basically monitoring if there's anything interesting in this stream and trigger the alert to Slack. In this case specifically, we like to monitor the node status. If there's a node which is offline, we like to trigger the Slack alert. So here's the definition of the scheduled task. So user can create a task, which is in this case we have fresh node states, and the scheduler interval is like 5 seconds. Every 5 seconds, it runs this query automatically in the background. This query is basically a table query or historical query. It runs to the end, run this query, and sending the result of this query to the target stream, which is node state. And then on the other hand, our alert, we're basically monitoring this stream if there is anything of the node which is offline and trigger the alert. So let me show the demo real quick. As usual, we have a Timeplus cluster, 3-node cluster, and which is node 1, node 2, node 3. All of the node is online so far. So we go to the console SQL editor. We query the Timeplus cluster to see the node status, which is online. All of them are online. And also we create a target stream, basically holding the results, cluster ID, node ID, and node state. And then we create the task. The task is basically collecting the data from system cluster every 5 seconds. And if it is running for over 2 seconds, it's basically terminate. And select this query and push the data to the target stream, which is node state. Run this query to create the task. And then we can start monitoring if there's any new data in this stream. So because it's the periodic is basically 5 seconds. Every 5 seconds, we will have the new data flows into this target stream, which is node state. We have 6 data points already. And then we can create a Python UDF function, which basically interact with Slack, because in order to trigger the alert to Slack, we are using the Slack SDK, Python SDK. We create a web client, and also we can send in the data, post a message to the chat, to Slack chat channel, which is basically the offline nodes. We can create this function, Python UDF function. And after we create the Python UDF function, we can create an alert. The alert is basically doing some of the whole pipeline is like creating the data from cluster into the intermediate node and also trigger alert. The alert is basically batch 5 events in one single alert batch. And also we can call the Python function to trigger the alert. The alert is basically bounding to a streaming query, which is basically incrementally in real time monitoring if there's any node state which is offline, which is not online, basically offline or decommission. And we can query this stream as well to real time in the console to see if there's anything wrong there. And what we like to do next is basically decommission one of the pod, delete the one of the Kubernetes pod to emulate one of the node will be offline. The alert are already triggered, so node 3 is offline already. And also in the Timeplus console, we have seen the 2 data points regarding the offline message. So if we go to the Timeplus console to take a look at the whole cluster status as well, so this cluster page will be refreshed a little bit later. So node 3 is basically offline. And if we wait a little bit, because the Kubernetes will be bring up the node automatically. So if we wait a little bit of time, so the node will be brought back online as well. And the cluster will be auto recover from this pod crash or pod deletion. Now this is pretty much the demo of the task. So from this demo, we can see how the task and the streaming query processing and also alert and the Python UDF glue the whole story. Very sleek, and also very convenient in Timeplus as well. User do not need to run another Python UDF elsewhere. So everything is maintained in Timeplus. So this is super convenient, super convenient. So next I like to go through the Timeplus Enterprise feature, which is we have quite a lot of new enhancements and also performance improvements as well in this release. So as usual, in June we have quite a bunch of updates and also enhancements in July, and we have Timeplus Enterprise 2.2 G8 already. And also in the latest preview release, we have quite a few enhancements, like schedule task we have demo just a while ago. And also we have mutable stream enhancement, novel key column, and also monotonically increase the integer columns as well. So per event emit, which is another emit strategy, which is added to the core product. So user can dynamically change the log level at runtime. So we will delve into the requirements, custom requirements for this one. Also, we have quite a lot of performance enhancements and add more functionalities as well. So in August, we will have more. We have more scheduled in the pipeline, like lightweight updates, collecting a pan stream, also materials will auto rebalance, and also other S3 based checkpointing stuff. There's quite a lot of more in the pipeline. So regarding the scheduled task is basically resolved to two major use cases. Number one is just like similar to ClickHouse refresh the materials view, periodically run some query and sending the query result to the task stream periodically to refresh the task stream. This is one typical use cases. Another use case is basically we like to make it work like a scheduled data collection. So for example, if you like to collect data from an external system, and user can create a scheduled task. The scheduled task can call Python UDF, and the Python UDF can interact with the external system to collect the data and send the data to the stream in Timeplus. And then we can do the further Timeplus data processing, like using Timeplus Materialized View, and also using Timeplus alert, like we demoed, and also this is basically the whole typical data processing pipeline by glue the tasks, Timeplus stream, Timeplus Materialized View, and Timeplus alert in one place in Timeplus. Per event, emit. So Timeplus has a lot of event emit strategy. So in this month, we have customer requirements. Basically, they like to emit per event instead of periodically emit or emit on updates or emit on in batch way. So this emit per event is basically for every event trigger the emit, the aggregation, and also even during our aggregation. And that in that way, user can have more, real-time event tracking, and also they can get the result every single time they say event in the system, which is very, very powerful. And also for the mutable stream enhancements, right now we can support nullable key columns for the primary key or for the secondary index key. So in this case, in this example, we have primary key, which is nullable stream. We have a secondary index S, which is nullable int as well. So moving forward, user can create indexes for them. And also our customer like the monotonically increasing integer column, like the automatically increased column in MySQL table. And user can, in this example, we have a ID which is integer 64, and these auto incremental for the mutable stream. So for every primary key, for every single key, different key, the number will automatically increase in background by the system. So a dynamic change log level, could be very handy because sometimes Timeplus log could be very verbose, and there could be quite a lot of log flush to the system, and it can introduce quite a few burden to the log aggregator in production. So our user can we change the log level during when Timeplus is running? So here's the command. We enhance this support in this monthly preview release. So the user can basically using the system command to show loggers, and user can also set the log level globally for the whole binary of, or set the log level for the specific component. So here is some example. For example, in Timeplus core engine, we have different components, and show logs will show all the components logs. And in this example, user can basically set the log level for disk local as debug, and also for system metrics log for trace, for example. And also this command support the regex for the webcarded. And also user can use in the if user like to prefer REST API to change the log. We support that as well. So performance improvement, which is significant for some of the use cases. For example, one of the typical use cases is CSV file reader, so and the write performance. We have tested everything is in the GCP box. So for the write, we have 20x improvement because of parallelization, and also for the read we have more than 127% of increase for the throughput and or even for the latency. And the next one will be secondary index block filtering. So if we have lots of data and we create a secondary index for the append stream, and after the improvement, we can have better performance and efficiency because of it can improve the data as fast as possible. And for different query, the speed up can be different. For the first query, like the is in, this can using the secondary index to prune the data. It has like more than 100x speed up. And for the second one, which is a table query as well, so we can the speed up is like 3.37x, which is significant as well. So the system is basically becoming more performant and efficient as we go. And another customer requirement is basically like the ClickHouse connection pooling reduction. So the use case is so our customer had a lot of thousands of Materialized View, and some of the Materialized View are quite busy, but most of the Materialized View is not that busy. So if we create a dedicated TCP connection for each of the Materialized View in Timeplus, there will be too many TCP connection to the ClickHouse, and which increase quite a lot of burden to ClickHouse server or ClickHouse cluster. So with the improvement, we can reuse all the connection for the idle Materialized View. For example, if 70% of the Materialized View is pretty idle, so we can reuse the TCP connection. And the netting result is pretty awesome. We will have 50% to 80% of the connection reduction, which basically reduce a lot of workload for ClickHouse cluster. So in this month, we add a lot of more functions, which is also from our customers. Number one is basically UUID generation. So it's like a UUID 7, and which basically encoded the timestamp, sorted. The UUID is basically sorted, unlike the UUID 4 version 4, which is not sorted. This UUID is sorted. And user can extract the timestamp from the UUID as well, because the timestamp is encoded in the UUID. And we have the array partial sort and array partial reverse sort as well. So this is a very performant. If you have a very large array and you like to partial sort some of them, like top 3, for example, partial sort, you only get the top 3 sorted, the first 3 elements sorted. So in this case, we have 4 element array, and we like only two elements sorted at the very beginning. For the reverse one, we like to only the first 2 sorted at the very beginning, but in the reverse order. So this is for example. And it's not guaranteed the whole array gets sorted, but only the first n elements, which is pretty handy. So this is pretty much for today's update and for this month updates. If you have any questions and also suggestions, please join our Slack, and also you can go to our GitHub for our open source code engine as well to give it a start. Thank you so much.
Thank you, Ken.
Thank
Thank
you.
you, everyone.